Okay, let's, quick announcement. Let's do a sign-in sheet. Just, if you could just tear a sheet out and put your name on it, put today's date on it, just pass it around. That way I know who is here in case it comes down to like a little small bonus. Small bonus, maybe, for being here the day before Thanksgiving. Small.
Anything helps. Anything helps.
Okay, so a few things. I was looking at what we need to cover, and I don't want to rush through Chapter 8, especially these last few sections. I think it's going to eat up all of today and next week. So I don't think I'm going to get to Chapter 9. I don't want to try and rush that. So what I'm going to do is on the final, I'm going to offer a few bonus questions over Chapter 9. And what I'll do is I will send you a link through an email to some online lectures that I have over the Chapter 9 material. And that way, if you watch it and you want to do the bonus on the test, great. If you don't watch it, at least you know, like down the road, if you need to look at that, you have a place you can go and get it, okay? The material from Chapter 9 is not difficult. It's a little new, but the concepts are all reasonable, and there's more formulas than there are anything else. So I think most students can do okay with that. With that said, let's continue. We were starting 8.6, and what we were trying to do was take a look at a function and represent that function as a power series. So let's just pick up where we left off. So I have a function here, f of x equals 5 over 4 plus 3x. We want to try and express this as a power series. And remember, the big picture here is that any function, as long as it is behaving well, can be represented as a power series. Every function. The example I'm giving you here is very, very carefully picked because it falls into the format of this thing, which is where I started 8.6 last class, is anytime we see an expression that looks like this can be turned into the power series sum n equals 0 to infinity of x to the n, right? So long as the absolute value of x is less than 1, and that comes from the whole idea of the geometric series. So our job right now is to try and make this look like this so that we can use that formula. All right? So first thing I'm going to do is just take that 5 on top, pull that out front. Then I'm going to try and make this 4 turn into a 1. So I'm going to factor a 4 out. And when I factor that 4 out, it'll come out front as a 4 on the bottom. And then what will I have under here? 1 plus 3/4 x, right? We're getting closer, right? Getting closer. We just need that to be a minus. So we're going to look at that plus as being, this is a squeaky marker. Minus, minus. All right. Do you all agree? Okay, so now we can rewrite this using this formula. Now, I will point out that really we're treating this x almost like this variable expression. So whatever we get in here, like here, this whole thing, is just going to be replaced right here, right? So it's almost like a u substitution. It's like this u, if this was u and that was u, then that's our u, right? Negative 3/4 x. So this should become 5/4 times the sum n equals 0 to infinity of negative 3/4 x to the nth power. And it will only be this if what? There's a condition here. If the absolute value of negative 3/4 x is less than 1. So it's whatever that expression is, the absolute value of it has to be less than 1. So if our expression is that, then it has to be that whole thing here, less than 1. Now I'll clean this up a little bit. This is absolute value of x is less than 4/3. So I'm pulling the 3/4 out as a positive 3/4 and then multiplying both sides by 4/3. So as long as the absolute value of x is less than 4/3, then this expression is equivalent to this expression. All right, they're equivalent. So let's go ahead and this, last time I didn't do this, but this time I'm going to. I'm going to take this function, I'm going to say that it is equal to this series, but I want to actually start plugging some values in. So let's plug in 0. If n is 0, what do we get? This to the 0. Oh, you know what I forgot to do? Sorry. I want to separate those. Sorry. I want to make that negative 3/4 to the n, x to the n. So I'm applying the n to both the factors. And that just makes it look like a power series where you have c sub n in front and then x minus a to the n. Right? Yes? Okay, so now let's plug in n equals 0. If I plug in n equals 0, this is 1, this is 1, and then that's times 5/4. So the first term here should be 5/4, right? And now let n be 1. So if n is 1, we're going to get negative 3/4, right? X to the first power times 5/4. So it'll be minus, won't it? Is it going to be minus? Yes, minus 5/4 times that to the first power. See, I put the negative out here. And then x. Now let n be 2. Well, go ahead.
Sorry, how did you set that? How did you get that set up again? So 5/4 minus 5/4 times 3/4. What is that?
Okay, I'm just running through the different values of n now.
Oh.
So if n is 0,
I see.
right,
I see.
it kills this whole thing. Well, this all becomes a 1, and you get that. Then if n is 1, this will be negative 3/4 times x to the first power times 5/4, which is that second term. Now I'm going to let n be 2, right? If I let n be 2, I'm going to have a positive, aren't I? Because this right here is going to be positive. So I'll have plus 5/4 times what?
9/16.
Yeah, 9/16 x squared. Let's do one more. Okay, the next one will be minus, won't it? So we'll have minus 5/4 times, now we're taking this and cubing it, right? So what is that cubed? 27 over 64 x to the third plus dot, dot, dot. Yes? Okay, and then we could put these numbers together, or reduce, or whatever we need to do. We could put those, and those are just numbers, right? So this infinite polynomial is exactly the same as that function, so long as we're looking in this little window right here. So now I'm going to show you that visually here. Move it up a little bit. Erase all this. So right now, the red is this original function. Ignore that vertical line. Okay, it's just that rational function. And right now, I'm approximating it with 5/4. See that? Which is just the first term. And that's this constant function, which isn't very good. So now I add another piece to it. 5/4 minus 15x over 16. That's this piece right here, added on, right? And now I have this line, which is still sucks. So now I do another one, right? Now I'm going to have a quadratic. So there's my quadratic right there. That's better, right? And also notice if this is 0, I said the absolute value of x had to be absolute value of x had to be less than 4/3, right?
Yep.
4/3 is 1.3 something. So here's 1. So 1.3, I don't know, is somewhere around in here. And then negative 1.3 is somewhere around in here. What's up?
You said x is greater than 4/3.
I said x, absolute value of x is less than 4/3.
originally you had absolute value of negative 3/4 x is
Less than 1.
less than 1, and then you did the flip, so it was.
I didn't flip.
Okay.
Yeah, because it's an absolute value, you don't flip anything. Okay, so what we're saying is that this polynomial should match up with the red function so long as we're like in this little window. So now I'm going to go and do another term. Now here's a bunch of them. And would you agree that between about here and here, they're matching up pretty good? Yes? And if we could go forever, they would be the same function, so long as you're on that little window. Okay. Any questions? Because I'm moving on to the next example. Okay, so for the next one, we have x to the 5th. I feel like I did this one. Did I not? Check in your notes. I didn't do that, did I? Yeah, okay. So this one, no? Okay. So look at this one. So our goal here, again, is to try and get this. Let me write this over on the board over here. Our goal is to try and get this to look like 1 over 1 minus x, which is the sum, n equals 0 to infinity of x to the n, so long as the absolute value of x is less than 1. And then also the end goal here is to have a power series that looks like that, okay? All right, so we're using that top one to create that. All right, so first thing I'm going to do here is I'm going to pull the x to the 5th out and then rewrite that like this. It's kind of like what we did on the previous problem with that 5. And then I'm going to pull a 2 out of the bottom. Right, so factor 2 out, and then one last step, minus minus. So this is going to become 1/2 x to the 5th times 1 over 1 minus negative 1/2 x. And this piece right here can be rewritten using the power series. Do y'all agree? Okay, so this is all going to become 1/2 x to the 5th times sum n equals 0 to infinity of negative 1/2 x to the nth power, and this is only valid if negative 1/2 x is less than 1, the absolute value, which means the absolute value of x must be less than 2. Yes? Okay. Pardon? Yeah, so I'm going to split this, but then I also need to deal with this. Now before that was just a constant, right? But this has x's in it. So watch what I do here. I'll leave the constant on the outside, but I'm going to push the x to the 5th to the inside. Now just bear with me for a moment. I'm going to split this up. Okay, split this up. Right? Splitting that becomes this, but the x to the 5th can come inside because, look, x is a variable, right? We agree? But the summation has n in it, so n is not impacting x. It impacts this x, doesn't it? But it doesn't impact this x because this expression doesn't have an n there. So I'm just going to tack it onto the end of this like this. Do you all agree? And now I can do something with that. These two I can put together, right? Add the exponents. There you go. Now, this is where we run into a little bit of an issue. If we want it to look like a power series, we like them to start at 0, and we like this to be an n, right? Here we can't have both. We have to have one or the other. We either have to have it start at 0, right? Here it starts at 0, and this n is not going to be n, it's going to be n plus 5, or we can change this to an n, but then this can't be 0. And this would be fine to have this as an answer, all right? But you need to be comfortable switching it, so I want to go through that and switch it. Let's try and make this an n instead of an n plus 5. So what would I need to put here for n to make that n plus 5 become an n? N minus 5. So everywhere I see an n, I'm going to replace it with n minus 5. Okay? Everywhere I see an n. So this becomes sum, 1/2, sorry. 1/2. This n becomes n minus 5 equals 0 to infinity. And then this is going to be negative 1/2 to the n minus 5. And then x to the n, right? And now one more thing. What am I going to write for that lower limit on that sum? N equals 5. So now your power series looks like the appropriate form in terms of we have the power starting at n, but our index starts at 5. They generate the same exact series, though. They give you the same thing. So one more thing. Let's write out a few of these terms. And I guess we can use this one. All right, let's use this one. So this equals, okay, if we plug in n, where am I going to start? At 5, right? I'm not going to start at 0. I'm going to start at 5. So I get 1/2 times, let's see, 5 here at 0, right? So that's going to give me a 1. And then x to the 5th power. So it's just 1/2 x to the 5th. So when we start to approximate this thing, right, with this series, the first term we have is a 5th degree power function. Okay, is the next one going to be plus or minus? We're plugging in 6, right? So when we plug in 6 right here, we're going to get a 1, which is going to make it a minus. So we have minus, we have a 1/2, that's coming from here. But then the 6 in here made that a negative 1/2, so I'm going to have times a 1/2. The negative is accounted for. X to what power? 6. Okay. What's the next term? Plus or minus? Plus, we're plugging in 7 now, right? So we'll have the 1/2 that comes out of the very front. And then we're doing 7 here, so it's this thing squared, right? Which gives you the 1/4. And then x to the 7. And then you can keep going, yes? I'm going to stop there. I'm going to put plus dot dot dot, even though the next term is negative. I'm going to put plus there. Okay? And then, of course, we can put this together. That's 1/8, that's 1/4. Let's take a look at this one. This should only be valid between what? Basically between 2 and negative 2. Let me zoom out here. So this is the original function, all right? And then here comes my approximations. So y'all pay attention to that right there. So I've got to go out. I'm not getting anything for the first 4 because it starts at the 5th power, right? So there we go. That's this one right here, 1/2 x to the 5th. And that's actually not that bad already, is it? It's pretty good. And then we just keep going. The next one's going to be better. So you see the dotted ones? Those are like the old ones, right? I'm leaving the old ones there, and you can see how they're kind of like getting closer and closer, trying to converge over to that red function. Do y'all see it? But it's only going to be valid between here and here, in between there. All right. Next one. I'm not going to do that one. Wait a minute. Yeah, okay, yeah, we're done with it. So the good news there is that if our function looks a particular way, right? If it looks a particular way, we can use that formula, right? But again, the chances that our function looks like a particular way are not very good. So we actually eventually need to have a way of getting the power series more efficiently, right? Which we will, it's the next section, but we're not there yet. All right, so now we have this thing called term term-by-term differentiation. This is a theorem. All right, suppose f of x equals sum n equals 0 to infinity c sub n times x minus a to the n. Suppose we have a power series with capital R greater than 0. What does that mean? That's right. This means, what we're saying here is that our radius of convergence is a positive number bigger than 0, which means that, remember with power series, there's 3 different ways it can converge. It can converge at a single point, on an interval, or everywhere, right? If we say that the radius of convergence is greater than 0, that means that you're either looking at an interval or you're looking at the entire number line. If you have convergence at a single point, how wide is a single point? It's not. There is no width. So the radius of convergence of a power series that converges at a single point is 0. So this is saying we are not looking at the case where we have convergence at a single point. It's interval or everywhere. So let's just say we have a function that behaves that way, okay? Suppose that's true. Then, of course, f of x is then c sub 0 plus c1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed plus c sub 4 x minus a to the 4th plus dot, dot, dot. That's just me expanding this out, right? That's me plugging in 0 here, plugging in 1, plugging in 2, plugging in 3, plugging in 4, right? That's all that is? Okay, so if that's true, then that's true. And the derivative of this function should then be what? Okay, so what's the derivative of a constant? 0, right? Derivative of constant, 0. All right, what's the derivative of this term right here? So c sub 1 is a constant, right? So it's going to come along for the ride. What's the derivative of x minus a? 1, right? Because x is our variable, a is a constant. So derivative of x is 1, derivative of a is 0. So what should we get as our first term in our derivative? C sub 1. Okay, plus. Now, here, what happens? This constant comes for the ride, right? But we have to take derivative of this, which is chain rule. So 2 comes out, 2 times this to the first power, but then times the derivative of what's inside, which is 1. So we should get 2c sub 2 x minus a. And then let's see what happens on the next derivative. So now, same thing, right? 3 comes out, joins the c sub 3. X minus a to what power? Squared, and then times the derivative of what's inside, which is still 1. And then this is just going to continue, right? Plus 4 c sub 4 x minus a cubed. Plus dot, dot, dot. Do you all agree with that? But this can be rewritten as a summation, okay? But because c sub 1 is where we're starting, I'm going to start my index at 1 and go to infinity. And let's see what pattern we have here. It's c sub 1, c sub 2, c sub 3, c sub 4, c sub 5, c sub 6, right? But what about the numbers in front of those? Like, what's the number in front of the c sub 1 here? 1. What's the number in front of the c sub 2? 2. C sub 3? 3. C sub 4? 4, right? So what the number in front is controlled by n, right? So this should just be n times c sub n, and then x minus a to what power? Close? Oh, n minus 1. N minus 1. Let's see, do y'all agree that this works? If we start at n equals 1, then we're going to get 1, right? C sub 1, and then x minus a to the 0, which gives us that first one. If n is 2, we get 2, c sub 2, x minus a to the 2 minus 1, which is 1. And then this would continue, right? Yes? So if you take a step back and look at that, that should look familiar. It does, right? Doesn't that look like the good old power rule? Like if you take the derivative of x to the n, right, it's n x to the n minus 1. That's a good old power rule. Okay, but look at this right here, this expression. If I just take the derivative of that expression and you use the power rule, what would you get? The n would come out, right? And then you'd have x minus a to the n minus 1. And voila, that's what you have here, isn't it? There's one little thing on this, though. Your index is starting at 1. So remember that. When you take a derivative of a power series, you can use your power rule, but your index needs to jump up by 1. Now, it would not be incorrect to put n equals 0 there, because if you put n equals 0, you still get the same thing. Do y'all see that, though? Because if you plug 0 in here, your first term's gone. So it's not incorrect to put 0, but I want you to remember that it changes to 1. That's pretty cool, right? We have power series. We can just differentiate the same way that we did back here.
So on the like a normal question, you would give us the f of x function and then ask for
what's the derivative?
The derivative.
Well, I wouldn't ask you that. Well, just hang tight. You'll see how we're going to use this. Yes?
You said that sometimes there's some problems that don't start at 0, like n equals 0, so we just shift up by 1.
We just shift up by 1. Yeah. Okay. Now, shit. I erased the piece I wanted to keep up there, but it's all right. I'll just rewrite it. Okay, so now let's go term by term integration. So what if we want to integrate a power series, right, instead? So let me start with the power series. Say it has a radius convergence that's greater than 0. Let's write out what the power series is. All right, let's try and integrate this now. So if we integrate this function with respect to x, okay, let's think about something first. Anytime we do an antiderivative, we're going to have a constant of integration, aren't we? Plus c at the end, right? But because this is an infinite series, I can't put a plus c at the end because it goes forever, right? So for the first time ever, I'm going to put the plus c at the beginning. Okay? So c. That's not one of these, okay? That's the constant of integration. Plus, now let's start integrating this term by term. Okay, what's the antiderivative of c sub 0? C sub 0x. Right? Because c sub 0 is a constant. So if it's like the number 3, the antiderivative of 3 is 3x. Okay, plus, let's see here. How would we integrate this? So maybe we should do this on the side. Pull the c1 out, because that's a constant. X minus a, like that. Yeah, so this you could do like a little basic U substitution. I'm not going to go through all the work on this, but you would get c sub 1 times a half x minus a squared. So just double check that this works. If you take the derivative of this, the 2 comes out, gets killed by the 1/2, right? and then you reduce the power down. And so if you take derivative of this, you should get back that. Do you all agree? Okay, so the next piece is going to look like this. 1/2 c sub 1 x minus a to the half. Right, that's this piece integrated. Or I should say that's this integrated. What about the next one? You'd follow the same logic. So what would it be? Integrating this one right here. 1/3 c sub 2 x minus a to the third, and the next one will be 1/4 c sub 3 x minus a to the fourth plus dot dot dot. Do y'all see how that's working? Now let's rewrite this as a sum. Equals c plus sum n equals, let's see where we're going to start. Oops, I just gave it away. Okay, right, we're working on trying to rewrite that. So look at my c's. C sub 0, C sub 1, so I should probably start at 0, okay, and go to infinity. And then let's talk about what's going to be in here. We're going to have C sub n, right? That for sure. That'll take care of this, 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 this. What about the x minus a? What about x minus a? X minus a to what power? What's that? N plus 1. So let's see if that works. N plus 1. So if n is 0, right? If n is 0, what do we get? C sub 0, x minus a to the first power. Is that what we have here? We don't have that, do we? We don't have that. Do y'all agree? But we do. Because what we're saying is our first term should look like this. C sub 0 times x minus a to the first power. That's what it should be. That's not what we have. But I'm saying we do because look, this is c sub 0 times x minus c sub 0 times a. Isn't that what that is? If I distribute the c sub 0 through? But what is this? It's a constant. I've already got that covered. See, there is a constant out here. We don't know what it is, but it's there. So it's taken care of kind of sneakily. It's taken care of, all right? So this is valid. This is still valid. Now, what about the next piece? If I plug in 0, we said we're good, right? If I plug in 1, let's see if we get this. C sub 1, x minus a to the 2, yes, but what about that? That's not there. So I need that to be 2 here, but that's the same as the power there, right? This 3 is that power, this 4 is that power. So what should I put out front here? 1 over n plus 1. Kind of cram that in there, but c plus sum n equals 0 to infinity, 1 over n plus 1 times c sub n times x minus a to the n plus 1. And does that look familiar? Yes, that looks familiar. Because if we take the antiderivative, right, of x to the n, the formula is 1 over n plus 1, x to the n plus 1, right, plus a constant. And that's essentially what happened here. We had like something to the power n, and what did our answer turn out to be? 1 over n plus 1, that thing to the n plus 1. Don't have to change the index for integration. For integration, you leave it at 0. For differentiation, you change it to 1. Okay? All right, are you ready? It's about to get messy. So that theorem says basically that if you have a convergent power series, you are free to differentiate term by term and integrate term by term. You are allowed to do that. All right? That's what the theorem is stating. But it has to be convergent on an interval or on the entire number line. All right. Okay, I want you to think about that for a minute.
Would that also be written, quantity 1 minus x to the negative squared?
Yeah, sure, you can move it up.
Yeah.
Mhm.
And then you could do the derivative that way.
Derivative? I want that as a power series. Right? I want that as a power series. Now, we are going to wind up working with what I showed on the board with integration and differentiation. But this is like the problem I started class with. I'm giving you a function. I'm asking you to express it as a power series. The only thing you have is this, right? That's the only thing we have so far. So can you make that thing look like that somehow? The squared is a problem, isn't it? The squared is a problem. Now, how do you mean?
Like 1 minus x and 1 minus x?
Put them side by side, like this. 1 minus x times 1 minus x. We could do that. We could do that. Now, could we do a power series for each of those? Yes? But then you have to multiply those two power series together to create your power series. And how do you multiply two power series together? Well, we haven't done it. We will do it, but that's next week. All right? We'll multiply and divide power series next week. So right now we're not quite ready for that. All right? So we're going to go with a slightly different approach. The approach that we're going to take is this, and it's a little sneaky. All right? It's a little sneaky. But I want you to consider something. What?
I said witchcraft.
Yeah. What is the derivative? I'm sorry. Yeah, no, we'll do it this way. I want you to realize, okay, realize the following. What is the derivative of this? I know that's not this, right? But it's that. Agreed? Okay, so what is the derivative of that? Well, that's the same as 1 minus x to the negative 1, take its derivative, right? I just brought that whole expression up. And then now just use your little power rule. This is going to be negative, what? Negative 1 minus x to the negative 2, chain rule, times derivative, what's in here? Negative 1, right? So what is that? 1 over the quantity 1 minus x squared. Hey, that's that, right? Yes? Do y'all agree with that? So, in other words, what we're saying is that this function, f of x, is equal to the derivative of that, right? That's f of x. Is equal to that. Y'all agree? But this is a power series. We have a power series for this, don't we? What's the power series for this? It's that, right? So this is the same as saying the derivative of the power series, that power series right there. Are you following this logic? This is very, very important. The original function, we realized that it's the derivative of that thing that we like, which is actually rewritten as a power series, but we still need to take its derivative, don't we, for this to match? So what is the derivative of this power series?
N plus 1.
It's sum, n equals
N minus 1.
n equals 1. Why? We differentiate it, right? Look, we are differentiating this power series. 1 to infinity. And then now what we do is we just use our good old-fashioned power rule on this expression. So n times x to the n minus 1. Y'all see that? Now, a couple of things. This is a power series, right? I mean, it is a power series, but it doesn't look like the standard format. So we either need to try and get the n to be 0 or this to be n. Right now it's n minus 1, right? Let's go for turning that into an n. So what would I need to replace n with to make this n? Sorry. Yeah. What would I need to replace that n with to make that expression equal to n? I need to replace n with n plus 1, right? N with n plus 1. Everywhere I see it. Okay, let's do that. Sum. If I replace that n with n plus 1 and then solve for n, what would I get? N equals 0. If I replace that n with n minus 1, or n plus 1, I get n plus 1. And then x to the n plus 1 minus 1, which would give you n. There we go. That's a good looking power series right there. Now just for our own kind of, oh, you know what? I forgot to talk about when this is true. Like when this holds. Right here, from here to here, is only true when? When the absolute value of x is less than 1, right? Because that's this. And I didn't mention this when I gave you that theorem that said you could differentiate and integrate power series. The good news is that if you differentiate a power series, the radius of convergence stays the same in the derivative. And if you integrate a power series, the radius of convergence stays the same. So you don't lose anything by integrating or differentiating. Your radius of convergence stays fixed, all right, whatever it is. So this has the same radius of convergence as the original one did. Okay, so let's write out a few of these. And I like writing them out because it gives us a real feel for like what this is. It's an infinite polynomial, right? So what's our first term? If n is 0, what do we get? 1. Plus, if n is 1, what do we get? 2x. If n is 3, what do we get? Sorry, I skipped 2, didn't I? Yeah. If n is 2, what do we get? 3x squared, 4x cubed, forever. This function should look like this infinite polynomial on the interval here. Do you think it does? Okay, so the red one is the function, and here's -1, and here's 1. So as long as we're between here and here, these should match up. Right now I'm using 1, which is this approximation. Let's add a few more. There's plus 2x. See my line? It's a little better. And then we just keep playing this game, and it's going to start marching towards the function. See that? Okay? It's only valid between 1 and -1, though. Over here, it's really having a hard time, isn't it? Like our power series is really trying to like get there, but it's taking a lot. Over here, we got there pretty quick. Do y'all see that? Like it just went whoosh, right to it. But here, it's acting crazy. Okay, good? Good. All right, we move on. F of x equals natural log of x plus 5. Same instructions. Find the power series for that. and I'll give you a hint. Realize something. See if anyone can see it. Remember, all we have to work with right now is this. Yes, what do you got?
No, I'm scared.
Too scared. Oh, don't be scared. Don't be scared.
The antiderivative of 1 over x plus 5.
Okay. Okay, you're on, yes, you're on the right track. I think what maybe you were thinking was the derivative of that has like 1 over x plus 5 in it, right? Was that kind of what you were thinking? Let me put that on the board. If we were to take the derivative of that function, right, we would get 1 over x plus 5. Wouldn't we? And we could actually rewrite that as 1 over 5 plus x, which is the same as 1/5 times 1 over 1 minus negative 1/5 x. Okay, a whole lot of stuff just happened, right? Okay, so I flipped that, and then I pulled the 5 out, so it became 1/5, which left that with a 1 plus a 5th, and then I made the plus a minus minus. Right? Y'all agree? Can we get a power series for that? Yes. Let's see what that is. That would be 1/5 sum n equals 0 to infinity of negative 1/5 to the n x to the n. I went ahead and put the negative 1/5 x to the n, and then I split it already. When is this valid? This is only valid when? The absolute value of x is less than 5. So I've already done this. I put that absolute value of that less than 1, and then I multiply both sides by 5, basically. Do y'all agree with this? Okay. I'm with you. But what? Are you just waiting for the shoe to drop? Well, so what we're saying is that the derivative, right? The derivative of that function is this. We're not looking for the derivative. This is the power series of the derivative. We want the power series of the function. So take the antiderivative of this, right? If I take the antiderivative of this, right? The antiderivative of this is that, right? So I just need to take the antiderivative of that power series, and I will get back that. So this is, I'm going to write it this way. This up here is the antiderivative of 1 over x plus 5, which is what you said, right? I just did this to help illustrate like how we get to the power series. But all in all, this is the antiderivative of this. But that means take the antiderivative of that, but that's a power series that we've just written out over here. I forgot the 1/5. I'll put it inside. Doesn't hurt to do it inside. 1/5, negative 1/5 to the n, x to the n. Right? Do y'all see that? And now how do we find the antiderivative of a power series? We use the power rule, right? We use the power rule. Now this right here is our c sub n. Okay? So that, when we do the antiderivative, that doesn't get touched at all. Okay? This is our c sub n. And then this right here is our x to the n. So this is where the power is going to go up. All right? So you all ready to do it? Do I write the integral sign anymore? No. Okay. So I'm going to say that this equals, ooh, that's a good blue marker. This equals,
The little things.
this equals, what's that? What? Before that. Constant. Plus c. Okay, so it's an antiderivative, right? C plus, now I'll pull the 1/5 at the end. But now it's going to be sum. Do we need to change our index when we're integrating? No. N equals 0 to infinity. Now, c sub n should stay exactly the same. But I should have a 1 over n plus 1 in front. So I'm going to go 1 over n plus 1 times, now here's c sub n, so I'm just going to slap the whole thing there. 1/5 times negative 1/5 to the n, and then what? X to the n plus 1.
You didn't do n plus 1 for the negative 1/5?
We did not do that. Yeah, so that's what I was trying to say. Remember, this right here is c sub n. This is not impacted by the power rule.
My bad.
Okay? Now, it's important that, you got that?
Yep.
Okay. All right, there it is. That's our power series. Now, let's write out a few terms. So this is going to be equal to some constant plus. All right, let's let n be 0. If n is 0, we get 1, 1/5. Negative 1/5 to the 0 is 1. So we're getting 1 times 1/5 times 1, and then x to the 0 plus 1, just x to the first power. So 1/5 x. Okay. Next term. We're going to plug in 1 for n. So this is going to be 1/2. And it's going to be negative. I know it's negative because when I put a 1 in here, I'm going to get a negative out of this one. So I'm going to go ahead and put the minus now. Minus 1/2 times 1/5 times 1/5, right? So this became, because I'm plugging in 1, 1/2, 1/5. That to the first power, you get a negative that comes out, and then here's your other 1/5, and then x to what power? Squared. Okay, the next, let's just do one more. Plus, this will be a positive. Now I'm plugging in 2, so 1/3 times 1/5 times 1/5 squared, 1/25, x to the, I'm on 2, right? So third power. So this should be c plus 1/5 x minus 1/20 x squared plus, what is that? 125, 375, 1 over 375 x cubed plus dot, dot, dot. There it is. That's our power series. Okay? Shall we check? Shall we take a look?
I think 1/2 times 1/5 times 1/5 is 150. Isn't it?
1/2 times 1/5 times 1/5.
Yeah.
Oh, why did I put 20? Yeah, 50 is right. Sorry. Is that why y'all were mumbling? Okay, yeah, I don't know. Yeah. I know what I did. And I'll be punished in math hell at some point in time, and that'll be a minimal thing that I get punished for. Okay, so here it is. Oh, I must be zoomed way.
What would be your baseline for math L? It's like just a room full of students who can't.
They ask incessant questions like, why didn't you integrate C sub n?
I'm not sure what it would look like. No.
Like, yeah, I know.
Yeah. No. My math hell has nothing. It doesn't have to do with teaching. It just has to do with all the things I've done wrong in math. Like just coming back and haunting me somewhere.
How dare you not flat out correct.
All right, so there it is converging. You can see it. We didn't look at the interval of. No, we did. It was between 5 and -5, right? Yeah, you can see it right here. I was going to say something. Oh yeah, I was going to show you something. So this is going to be a little depressing, what I show you. It's depressing, but it's also, I don't know. You can give me your opinion. So I'm going to go to Wolfram Alpha. Oops. Go to Wolfram Alpha. Maybe. Just ignore that.
Could be worse like this.
Yeah, no, I just ordered a little cheapy CNC machine. It's real cheap, so I don't know how it's going to work, but I was watching a video on setting it up, and the guy was doing a Chuck Norris thing. I don't know why. Okay, so I'm going to type in natural log of x plus 5. Okay? All right? That's all I'm going to do. Type it in. Let's just see what happens. Okay, I'm sorry if I'm blocking you here. So, okay, there's a plot of it. All right. Come down here. There's the root of it. There's some properties. It's bijective. Oh, what is that? What is that? What is that? That's the power series. So we just found. Now this is the constant plus c. They just picked an arbitrary constant, but, well, they didn't. They wanted the value of this polynomial to be equivalent to the log function at 0. So
Is it infinite with that 0? Is that an
yeah,
octal or a
so
0?
this is an O. This is just saying, you know, we're stopping at order 6 and just stopping. But you could get more. And this is basically for any function you ever type into Wolfram Alpha, that will always give you the power series. So if I type in sine x, hit enter, it's going to give me the series. Now it's not giving me the whole thing. It's not giving me the formula, right? It's giving you the first few. Yeah, just ignore Taylor. We'll talk about that. That's next class. See what it says here. Information. Big O notation. Big O has to do with, yeah, we use this. You can read about it here. Computer science, big O is kind of a big deal. Kind of? Kind of. It's like operation count type stuff, right? It's the order of, I think, basically how hard your CPU is working, I think. Yeah, so is it going to take a lot of operations or not? And I think they do different orders of like linear and quadratic. Yeah. Okay. Moving on. Okay, for this one, I think I'm just going to, no, I have to. No, I'm just going to set it. No, God, I'm going to have to work it out. Damn it. I'm trying to save us time, but it's like all these little things you have to see. Okay, so how about this one? X plus 2 over 2x plus 1 times x minus 1. So we want to find a power series for this. So we just go to Wolfram Alpha, right? I mean, it's just amazing to me, the power that we have now, you know, just crazy. You can go to a website and get the power series by just typing in something. It's nuts. Okay. Yeah, so if we're trying to do it without Wolfram Alpha, then we have to somehow make it look like this, but I don't know, maybe that's the derivative of something or the antiderivative of something. It doesn't look very nice. So you sit there and you look at it for a while, and then you realize that this is equal to 1 over x minus 1 minus 1 over 2x plus 1. And how do you think that happened? Partial fraction decomposition. So you remember partial fractions? So you have to split that up. So this is where you have to go and set it up and be like, you know, this is two distinct linear factors, so this is going to look like a over this plus b over this. Then you go solve for a and b, right? Okay, so let's say we get to that. Now each of those I can use a series.